Hello everyone, I'm Yuan Shi. It's my great honor to attend this conference and do my report here. The topic of my report is liquid cooling system optimization of data center server by considering mostly ambient temperature and humidity. My report is divided into 4 parts. First, let's start with the background. With the advent of big data era, the data center industry is developing rapidly, which drives the performance of information technology improves continuously. High heat flux and high energy consumption have become two key words in this industry. At present, the traditional air-cooled technology has become difficult to meet the heat dissipation of the servo cabinet. Therefore, the water-cooled technology with high heat transfer coefficient and small volume has attracted the attention of scholars. Moreover, the cooling system accounts for about 40% of the total energy consumption of the data center, so the most effective way to reduce the energy consumption of the data center is to reduce the energy consumption of the cooling system. Through the review of previous studies, many people only researched the inside system cabinet, or only researched the external cold source. We found that they were not comprehensively considered the internal thermal management optimization of the system. So my research is comparing the inside system cabinet with the external cold source and consider the impact of local climate, such as ambient temperature and relative humidity on system operating conditions. Second part is the model and calculation. Use the fan-topped water-cooled heatsinks to solve the heat dissipation of the chips in the server cabinet and optimization the working condition parameters of the cooling system based on the cooling tower with the thermal power of 4.8 kilowatts and analyzes the energy consumption of the system under its operating condition. The intercooling system is divided into internal and external circulation processes. The internal calculation involves the secondary cooling water flowing into the server cabinet to remove the heat of the chips, leading to the heat exchanger to cool down, and then flowing into the server again. The external circulation involves the primary cooling water from the cooling tower entering the heat exchanger and then returning to the cooling tower to cool down. The primary and secondary cooling water exchange heat by the planet heat exchanger. The whole system, including analog servo cabinet, control measuring cabinet, and the water cooling system. The analog servo cabinet is composed of 12 analog chips and corresponding 5 radiators. The thermal load of each CPU can be controlled by adjusting the heating port of the sequential heating plant connected to the analog chip software and connected to the control module cabinet by variants. The control module is equipped with the power supply and its power adjustable accessory equipment, which can adjust the thermal load by adjusting the power supply. In addition, the control module cabinet can display the temperature and mass flow data transmitted using the temperature and mass flow meter sources in the experimental system. The structure of the water cooling system is shown in figure, in which the pump uses various frequency motors to save energy. However, considering the low fan power of the cooling tower for convenience and the cooling system, the cooling tower with a fan without a frequency converter is selected. In addition to mass flow meters with mass flow regulation function and some temperature sensors, including thermocouples and PT100 sensors, and are used on the test bed. In the experiment, the thermocouple is mainly used to measure the chip temperature, which is placed between the bottom of the radiator and the upper surface of the chip. The PT100 sensor is mainly used to measure the inlet and outlet temperature of the plant heat exchanger. The digital power meter is used to measure the pump power. The table lists the main parameters of the equipment and measuring sensors used in the water cooling system. Figure A is a heat dissipation spectral unit of the servo cabinet, showing in order from the bottom of the top are the chip's bottom planet of the heatsink. Figure B is the bottom planet of the heatsink. Figure C is an enlarged parallel view of the fan. Those formulas are used to obtain the relationship among the water inlet temperature, the optimal flow rate of secondary cooling water, and the safe chip temperature. Next part is results and discussion. Firstly, we analyze the secondary cooling water heat management through transit simulation and thermodynamic calculation. It was observed that the chip temperature, the T-chip, is related to the servo inlet temperature T1 and the water flow of the secondary cooling water QV2. With the increase of QV2, the chip decreases, and the decreasing region of the chip temperature becomes smaller. When the QV2 greater than 18.1 liters per minute, the change of T-chip almost tend to be stable. As the T decreases, the radiation rate of T is basically the same. The volume of QV2 is determined by T1. QV2 increases with the increase of T1. The relationship current between QV2 and T1 can be used to design secondary cooling water heat management. Then we studied primary cooling water heat management. QV1 is affected by ambient temperature and relative humidity. In May 20, the ambient temperature was 12.1 centigrade and the relative humidity was 46 percent. QV1 will decrease first and then increase with T1. QV1 is affected by T1 and QV2. The volume of QV2 is determined by T1. Choose selected the T1 and the QV2 is stationary. The system power and PUE decrease first and then increase with T1. Under a specific ambient temperature and relative humidity, there is an optional T1 to minimize the system power and PUE. In May in Tianjin, when the ambient temperature is 22.1 centigrade and the related humidity is 46 percentage. And the optimal combined inlet temperature is 19 centigrade. The system power was 0.1845 kilowatts and the POE was 1.0384. Finally, we started the system under annual working conditions heat management. When the ambient temperature was too low, it caused problems such as the humidification in the data center. The ambient temperature in January, February, and December was smaller than 5 centigrade, so we only considered the March to October. The working condition in those months in this study, T1 QV1 was affected by the ambient temperature and the relative humidity, and the QVR was affected by T1. High ambient temperature and high relative humidity will cause those values to increase. In July in Tianjin, those values have maximum values because the ambient temperature and the relative humidity in Tianjin are the highest in July. System power and PUE was affected by the ambient temperature and relative humidity. The system power and PUE will increase with the increase of ambient temperature and relative humidity. Low ambient temperature and low relative humidity help to reduce the energy consumption of the system, which is more conducive to the thermal management of the system. Through the above research, the following conclusions are obtained. The safety temperature of the chip was set at 17 centigrade, and the maximum water of carbonate was 34 centigrade. The result based on this show that the ambient temperature has significantly impacted the operating conditions of the system. At high temperature, the system required more power to cool the chip. Therefore, the primary water flow, secondary water flow, system power and PUE of the system increased. Those values decreased with the fall of the ambient temperature. With the two, we studied the operating conditions of the system when the relative humidity was 14 to 18%. The results show that a higher relative humidity indicates a lower ambient temperature that can be met by the maximized inlet water temperature of the cabinet. Under the same ambient temperature with the decrease of relative humidity, the common inlet water temperature corresponding to the ambient temperature gradually decreased, which further decreases the power of and the PUE of the system. 3. We studied the impact of the monthly average ambient temperature and the relative humidity on the working conditions of the system from March to October in Tianjin. The research showed that the working conditions of the system were significantly affected by climate conditions. In summer, when the ambient temperature and the relative humidity are high, the primary water flow, the secondary water flow, and the system power and PUE of the system increase. When the ambient temperature and relative humidity decrease, the values also tend to decrease. That's all. Thank you for your kind attention.